There's a hidden battle being fought all around us, every single day. It happens on a microscopic level, inside almost every single device you own. And it's all about one thing: creating the unbreakable bond. I mean, just look around you for a second. Your phone, your car, the stuff in your kitchen, they're all built with these incredible modern materials. But in this world of plastic, the weakest link is almost always the same exact spot, the point where plastic has to join with metal. And let me tell you, the stakes here are huge. A weak joint isn't just a cracked phone case. No, we're talking about a critical component failing under pressure, a seal breaking, a device just falling apart right when you need it the most. Every single one of those joints is a potential disaster just waiting for a reason to happen. So, to stop that from happening, engineers have come up with some seriously powerful techniques. And we're about to witness a showdown between two of them. Think of it like a clash of the titans. Two different technologies, two different ways of thinking, all fighting for the exact same goal: to forge that ultimate bond. So, in one corner, you've got the reigning champ, the established power, pre-molding. This technique is all about brute force. And in the other corner, we have the challenger, ultrasonic insertion. This one's newer, it's faster, and it's built on precision and, get this, invisible energy. The old guard strategy is pretty straightforward. You take a metal insert, you place it inside a mold, and then you just unleash this flood of molten plastic. It completely entombs the metal part as it cools down and gets hard. It's a bond born from just overwhelming heat and pressure. But the new challenger, its approach is something else entirely. It doesn't use a flood of molten plastic at all. Instead, it takes a piece of solid plastic and drives a metal insert straight into it using a focused beam of ultrasonic energy. This is a bond forged by pure high-frequency vibration. It's kind of like magic. And the beauty of it is just how slick it is. Okay, so the metal part just sits on the plastic. Then this thing called an ultrasonic horn touches the insert and starts vibrating like crazy, transferring all that energy. This creates such intense focused friction that only the plastic directly touching the metal melts. It flows perfectly into all its little grooves and then gets solid again almost instantly. So we have our two contenders. But talk is cheap, right? How do we prove which one is actually stronger? Well, we make them run a brutal gauntlet, a whole series of punishing, destructive tests that are designed to find the absolute, undeniable breaking point of each bond. The challenger's weapon of choice? An ultrasonic frequency of 20,000 vibrations a second. That's a frequency so high you can't even hear it, but trust me, it is immensely powerful. All that energy is delivered with 1,500 watts of power. That's enough to run a microwave, but it's all focused down into a single, tiny point. And it's all driven home with up to 3 bars of static pressure. That's about the same pressure you'd find in a car tire, just to make sure that insert is seated perfectly. Now, the bonds made by both methods are going to face 2 trials. First up, the pull-out test. This is just pure, raw strength. A machine is literally going to try and rip the metal insert straight out of the plastic. Then there's the stripping torque test. This one measures how much twisting force the joint can take before it gets violently stripped out. The source material describes this moment with this cold scientific precision, and it's almost chilling. It just says, the maximum torque at which metal insert is stripped out from mounting hole. There's no gray area here. There's only force, and then there's failure. So, the tests were run, the joints were broken, the numbers were crunched. The final verdict is in. After all the theory, all the preparation, all the buildup, it all comes down to this one simple question: which bond is going to hold? First up, the pull-out test. The old guard, pre-molding, holds strong under 10.4 megapascals. That's a huge unit of pressure, a really respectable number. But then, the challenger, ultrasonic insertion, it endures 15.88 megapascals. That's over 50% stronger, a stunning victory in round 1. And now for the twisting, the stripping torque. Pre-molding resists up to 12.5 Newton meters before it finally fails. But the ultrasonic bond, it holds all the way up to 21.63 Newton meters. That's more than 70% stronger. It's not just a win, it's a total domination. So, the big question is, why? Why did the new challenger win so decisively? Well, the answer isn't about brute force. It's about the really elegant physics at the heart of the whole process. The whole victory really comes down to this one concept, localized heating. See, unlike pre-molding, which basically heats up everything in sight, those ultrasonic vibrations create intense targeted heat, only at the interface, right where the metal and the plastic actually meet. That super-focused heat softens the plastic just enough for it to flow into every single microscopic groove and knurl on that metal insert. We're not just talking about a physical grip here. The plastic molds itself to the metal on a near-molecular level. The old pre-molding process, for all its power, just can't force the plastic into those tiny features with that same level of detail. Which leaves us with a pretty fascinating thought, doesn't it? We started out looking at a tiny metal fastener, and we ended up seeing how focused, invisible sound waves can create a bond that's way stronger than one made with just overwhelming heat and force. So if sound can do this, what other invisible forces are out there, just waiting for us to harness them?